The mystery of hypervelocity stars. How some stars escape the Milky Way. Imagine looking up at the night sky and knowing that some of the stars you see are not only moving, but they are also speeding so fast that they are on a path to escape our galaxy forever. It might sound like the stuff of science fiction, but it's a very real phenomenon, and these stars are known as hypervelocity stars. Traveling at speeds exceeding 1,000,000 kilometers per hour, these stars are defying the gravitational pull of the Milky Way and heading out into the unknown. But how do these stars achieve such incredible speeds? What sets them apart from the billions of other stars in the galaxy? And where exactly are they going? To answer these questions, we need to explore the complex forces at play in our galaxy and beyond. The existence of hypervelocity stars provides fascinating insights into the dynamics of the universe, revealing the immense power of gravity, the strange behavior of black holes, and the violent events that can shape the cosmos. In this article, we will dive deep into the nature of hypervelocity stars, the mechanisms that launch them to such incredible speeds, and the implications of their journeys as they leave the Milky Way behind. What are hypervelocity stars? At their core, hypervelocity stars are just like any other stars, vast, burning spheres of gas, composed mostly of hydrogen and helium, undergoing nuclear fusion at their cores. What makes them unique is their velocity. The term, hypervelocity, refers to stars that are moving fast enough to escape the gravitational pull of the Milky Way, a speed that astronomers estimate to be about 500 kilometers per second or more. For comparison, our Sun orbits around the center of the Milky Way at a relatively sedate speed of about 220 kilometers per second. Most stars in the galaxy are moving at similar speeds, and their orbits keep them bound to the Milky Way for billions of years. However, hypervelocity stars are different. They are traveling so quickly that they are essentially on a one-way trip out of the galaxy, never to return. Astronomers have discovered only a few dozen confirmed hypervelocity stars so far, but they believe that there could be thousands more out there, hidden among the vast expanse of stars in the galaxy. These stars are incredibly rare, which makes studying them a challenge, but also incredibly exciting. Every hypervelocity star tells a unique story about the forces that propelled it to such high speeds and the journey it is now on. The supermassive black hole at the galaxy's center. One of the most common explanations for how hypervelocity stars achieve their incredible speeds involves the supermassive black hole at the center of the Milky Way. This black hole, known as Sagittarius A, Sag A, has a mass of about 4 million times that of our Sun and exerts a powerful gravitational influence on the stars and gas surrounding it. The process that can launch a star to hypervelocity begins when a binary star system, two stars orbiting each other, ventures too close to the black hole. As the stars approach, the immense gravitational forces of the black hole tear them apart. In some cases, one of the stars in the pair is captured by the black hole, while the other is flung away at an extremely high velocity. This is often called the gravitational slingshot, or gravitational assist, effect. The star that is flung away becomes a hypervelocity star. Its speed is so great that it can escape the black hole's gravitational pull and continue outward, eventually moving fast enough to break free from the galaxy itself. This process is similar to the way NASA uses the gravity of planets to accelerate spacecraft during interplanetary missions, except on a much larger and more violent scale. This slingshot effect is one of the primary mechanisms by which hypervelocity stars are created. The interaction between binary star systems and the supermassive black hole at the galaxy's center provides a natural explanation for how these stars can achieve the speeds needed to escape the Milky Way. However, it's not the only possible explanation. Other mechanisms that create hypervelocity stars while interactions with the supermassive black hole at the center of the galaxy are one-way hypervelocity stars are created. There are other processes in the universe that can result in similarly high speeds for stars. One of these is the supernova explosion of a companion star. In a binary star system, where two stars are gravitationally bound to each other, one of the stars might eventually reach the end of its life and explode as a supernova. When this happens, the explosion can impart an enormous amount of energy to the surviving companion star, accelerating it to hypervelocity. If the velocity of this surviving star is high enough, it can escape not just the gravitational influence of the supernova remnant, but also the entire galaxy. This process is particularly interesting because it doesn't require the presence of a supermassive black hole. Instead, it relies on the energy from the supernova explosion itself to propel the star to hypervelocity. These stars, known as runaway stars can travel at extraordinary speeds and may eventually leave the galaxy behind. Another possible mechanism for creating hypervelocity stars involves interactions between galaxies. When galaxies collide or pass close to each other, the gravitational forces between them can cause stars to be flung out at high speeds. In some cases, these interactions could accelerate stars to hypervelocity, allowing them to escape both galaxies involved in the collision. These alternative explanations broaden the possibilities for where and how hypervelocity stars are formed. While the gravitational slingshot effect from the supermassive black hole is the most well-understood mechanism, it's clear that the universe has multiple ways to launch stars on their high-speed journeys. The journey of a hypervelocity star: once a star has achieved hypervelocity, its fate is sealed. It is on a one-way trip out of the galaxy, moving through the cosmos at incredible speeds. But what does this journey look like? And what happens to these stars once they leave the Milky Way behind? At first, the hypervelocity star will continue to move through the galactic halo, a roughly spherical region of space that surrounds the main disk of the Milky Way. The halo contains a diffuse collection of stars, gas, and dark matter, and extends far beyond the visible part of the galaxy. As the hypervelocity star travels through the halo, it will eventually reach the outermost regions of the galaxy, where the density of stars and gas is extremely low. Once the star crosses this boundary, it enters intergalactic space the vast, empty regions between galaxies. Here, the star will continue its journey, drifting through the darkness of space with little to slow it down. Intergalactic space is incredibly empty, with only a few stray atoms of gas per cubic meter. In this emptiness, the hypervelocity star will encounter almost no resistance as it travels, meaning it will continue moving at its current speed for billions of years. Eventually, the star will pass so far from the Milky Way that it will become essentially isolated, cut off from the gravitational influence of any galaxy. It will continue to burn for as long as its fuel lasts, shining as a lonely beacon in the vastness of space. Depending on its mass and composition, the star might live for billions of years, but eventually, like all stars, it will exhaust its nuclear fuel and die. The final fate of a hypervelocity star depends on its mass. Smaller stars, like red dwarfs, can burn for trillions of years before gradually fading into faint, cold remnants known as white dwarfs. Larger stars, on the other hand, might end their lives in spectacular supernova explosions, leaving behind neutron stars or black holes. Regardless of the exact outcome, the star will spend its entire life drifting through intergalactic space, far from the galaxy where it was born. How do we detect hypervelocity stars? Given how fast hypervelocity stars are moving, one might assume that they would be easy to spot. However, detecting these stars is actually quite challenging. Most hypervelocity stars are relatively faint, and they are moving through regions of space that are difficult to observe from Earth. Astronomers typically use specialized telescopes and instruments to search for hypervelocity stars. These telescopes are capable of detecting the faint light emitted by distant stars and can measure their velocities by analyzing the Doppler shift of their light. The Doppler shift is a change in the wavelength of light that occurs when an object is moving toward or away from an observer. By measuring this shift, astronomers can determine how fast a star is moving and whether it is traveling fast enough to be considered a hypervelocity star. One of the most successful missions in detecting hypervelocity stars has been the European Space Agency Gaia satellite. Launched in 2013, Gaia is mapping the positions, distances, and motions of over 1 billion stars in the Milky Way. This vast dataset has allowed astronomers to identify potential hypervelocity stars by tracking their movements over time. Even with these advanced tools, finding hypervelocity stars is like searching for a needle in a haystack. The vast majority of stars in the galaxy are moving at relatively low speeds, so hypervelocity stars stand out only when their velocities are measured with great precision. Nevertheless, as technology improves, astronomers are